When we talk about optimization, it's typically we optimize some function subject to some constraint. Let me repeat that again. You optimize some function value subject to the variable need to lie in certain constraint. So you need to know what? You need to know some kind of categories of different functions and categories of different sets. That's a constraint set. So you need to know these two pretty well, so you can categorize optimization problems into a few categories, and so that you can formulate your problem accordingly. Okay. So now let's talk about set and function. Those are very elementary. Okay. First type of function or mapping is called linear, the most basic function. Okay. The most one is constant, by the way. So you have a function, it's constant, it doesn't change, right? That's constant type of function. The next, the most general one, or the simplest one, it's a linear function or linear mapping. It must satisfy these properties. Well, I didn't say x and y has to be numbers or vectors or matrix. It can be any point, any set. Okay, we don't have to be over general, but in your mind, x and y can be scalar, can be matrix, can be vector. As long as it satisfies these two properties, then it's fine. Yes, that's true. There's a lot of typos. Great. Alpha fx. Okay, that's linear. So the first type of functions, those are examples, by the way. I don't think that covers everything. There's some examples. So this is a linear function. It's a matrix times a vector. It's a linear function of that vector variable. In this case, I say A is a rotation matrix. Right? This is a rotation matrix, but doesn't matter. That means rotation operator is also a linear operator. Then, Yinghan, how do we prove this? I say this guy is a linear function. How do we prove it? No, don't worry about notation. Well, this try to mislead you to something not important.
Oh, this is a linear combination.
No. I say f is a linear function. I ask you to prove it. You just need to check it satisfies the definitions of a linear function, right? Suppose I have fx plus y. I have x plus y. How do we do it? Ax plus y, because it's a matrix vector multiplication, is a linear operation. Y is fx plus fy. It's satisfied the first property. Of course, you can do the second one. So check definition is all you need. Okay. Now I want to jump a little bit to the next level. Is this useful in practice? I think no, not directly, but indirectly really useful. It's like a training your muscles. It's like that. Maybe Liu Ben. I have x here. Okay, this is a little bit more abstract. So this x is an integrable function of time. Okay, it's a function. It's like an infinite dimensional vector. It's not like Rn or R3 or R2. It's just a function. How do I define the mapping? If you give me a function, this x as a signal, I've returned you a value, which is an integral of that x function over time. Is this well defined? It's integrable function. Of course, it's well defined. Okay. Then I'm asking you, how do we prove this is a linear function of x? By definition. So let's say x, I somehow try to use a square bracket to distinguish this is not really a function of a scalar or vector, but that doesn't need to be, right? So this means integral of two signals, x and y. So x tau plus y and tau d tau, right? And so I can do the integration separately. The reason is integration is a linear operator. Why the integration is a linear operator? Because integration is nothing but summation. Even you see integration, you just say this is a summation. The reason you can say it is because you are not a mathematician, you are an engineer, you can just say that, okay? And it's 99% is always okay. So that will be x tau d tau plus y tau d tau, which is fx plus fy, right? So this is also a linear function. I want you to recognize things in a more abstract way. This expectation, I don't want to do that in this class. It's also a linear operator because expectation, well, we can write. Expectation is nothing but integral of the value times the probability of that value occurs dx. It's also an integral. So expectation, when we say random variables, expectation is a linear operator. Let's not worry about this too much. The next one is trace. Although I write it like x, but now this time I say x is in R n by n. Okay. Is this a linear function of x or not, Yinghan?
Yes.
Why?
Because I trace the x plus y.
Okay, it's a matrix, right? Let's use another variable if you guys are happy with other variable. Let's say trace A plus B equal to trace A plus trace B. Because trace all involve some summation. Summation is linear. Okay, and also trace of alpha A equal to alpha of trace A for any kind of scalar alpha. So trace is also a linear function. So when I say minimize trace of, let's say, x subject to something, looks weird, right? Minimize a trace of matrix subject to some constraints. But essentially what you're doing is solving a linear program. I just want you to not be confused by how complicated this variable is, but you rather need to focus on the nature of the function you are optimizing. If I say minimize trace of something, it's really minimize a linear function of something. This thing is the same or as simple as a linear program. This is a linear program that can be solved very, very fast. Okay. Now let's be a little bit more like a mathematician. So we start distinguishing linear and affine 仿射和线性啊. Sometimes there are a linear affine are often used interchangeably. I don't distinguish them that much, but typically, more precisely or more rigorously, affine mapping fx is a affine mapping if gx, which is defined as fx minus fx0, is a linear mapper for some fixed x0. Okay, if you define gx as fx minus some kind of fixed reference point, then gx is linear, then that becomes a affine mapping. So for finite state representation, this is just like that. For linear mapping, it's just AX. For affine mapping, it's AX plus B. So if you define GX like fx minus f, let's say 0, which is AX plus B minus F0, A times 0 is 0 minus B, so it's AX. So GX is just AX. You subtract this affine term out. Typically, when we say affine, why we often think about them as the same as the linear mapping? Because sometimes we can conveniently write them as it's called homogeneous representation. That's similar to our representation, the matrix pose, right? So we define a homogeneous coordinate. So x1, which is I call x tilde. If I introduce x tilde and I define a tilde as AB1, 0, AB01, sorry, then this guy function can be written as a linear form in homogeneous coordinate. Okay, move away from affine mapping to linear mapping, you need to introduce homogeneous coordinate. Those are very important basic tools for you to start recognizing the key nature of the optimization problem you're facing. Okay, now you don't see the connection yet. Later in this class, maybe not today, okay, later in this class, you will see a lot of these kind of techniques are pretty helpful. All right, now let's talk about sets. So function, we define a affine function, a linear function. And each of those functions actually defines a set through their sub-level sets. Okay, so that's the, typically when you represent any set, let's say you represent, so my tutorial on linear algebra, I talk a little bit about the geometry, how to represent the shape in computer. Well, maybe you can use grids, okay? But mathematically, any of these sets can be represented by some function less than or equal to 0, the sub-level set of that function. Okay, when we say a set is smooth, typically means the function representing the set is smooth. So set and the function are somehow tightly related. So let's see some example so you have a better feeling about this. Well, linear set, when I say a set is linear, it's nothing but, or a affine set, it's just we use this affine mapping sub-level set to define this, can be represented by a sub-level set of a affine function. So this is called sub-level set. Okay. For example, this guy, line on the hyperplane, is defined as, this is what? A transpose x minus b equal to 0. Well, this doesn't have an inequality sign, it only have the equality sign. So this is a function of x, and it's a affine function of x. So this set, I would say, is a affine set or a linear set. You see what I mean? Because it's a level, almost a level, they're not sub-level set, it's a level set of a affine function. So what does this mean? This means a line or hyperplane. Typically, when you say this, right? How to say? This is my, let's say this is x1, this is x2. This is my a vector, the normal vector, okay? How do you represent this line? How do you represent it? The line can be represented even in coordinate-free way. It's all the points. Let's say this guy, let's keep a point here. Let's say this is my x0. any other point, it will be x minus x0 orthogonal to A. So all the x satisfies x minus x0 orthogonal to A. And by our notation, this means A transpose, because inner product in vector in Rn is that A transpose x minus x0 equal to 0. That's orthogonality. That means A is perpendicular to any of this vector. Anywhere, no matter where you put this, it will be that, right? So that's basically of the form A transpose x minus A transpose x0 equal to 0. And this is my B here. Okay, this line is just can be written as a level set of a linear equality constraint. And if I say half space, that means Ax less than or equal to B. If you base on that figure, that will be A transpose X minus A transpose 0 less than 0 will be something like this. Will be half space. Maybe I'll ask Yangxing, is this half or the other half? Ax transpose minus Ax 0 less than or equal to 0. Is this half or the other half? How do you know? Choose the point test. Okay, great. Well, you do not try to memorize. You try to think. What does this half space mean? All the point. This vector should make a acute, not acute anymore, right? The angle should be bigger than half pi, so it will be less than 0 or bigger than 0. Huh? Less than 0, so that's this part. Okay, or bigger than 0 than the other part. Right? So you think, when you see figure, you think what the equation means. So typically the equation somehow should connect to geometry. And another key concept, especially useful for control and optimization, is its intersections of half space, which are polyhedron. Okay, in this case, this x is Rn, and this one is could be h could be Rm by n. The small h is Rm. So overall, you will say h equal to maybe let's say capital H1 transpose. This is the first row of it. H2 transpose, Hm transpose times x should be less than, this is H1, H2, Hm. So each row of H, if you multiply this actually imposes M inequalities, right? Times x less than this. So this imposes M inequalities. So let's say Hi transpose x less than small hi, this is a half space. Right, so that means this x need to be at the intersection of all these M half spaces. Okay, that defines a polyhedron. So I can draw some figure. So maybe the first row is Hx transpose x less than this. The second row tells me this. Then overall, I will have this region. Okay. So in this case, this is unbounded polyhedron. Many times I can have this, that, this. So eventually may have a bounded one. So bounded polyhedron, will be called polytope. But I don't think people use that very precisely. I often got confused, but just let you know, there's some kind of subtleties about polyhedron, polytope, polyhedra. Those terminologies sometimes confuse you, but I think you need to know bounded and unbounded. Sometimes they give you different result. Any questions? Then I will ask you, everyone, to be able to think about the following sentence. For matrix variable x, think about you have a space of x. Each point on the space is a n by n matrix. I gave you a matrix A. I say trace AX less than or equal to 0. In your mind, that should be a half space in matrix space. Stefan, does that appear to you, or do you feel? Let's not do that. If you don't like it, you can think about this half space definition, like for example, this is equivalent to say inner product of A with x minus x0 less than or equal to 0. Inner product. So as long as inner product is defined, I can define half space. Half space is nothing but angle, right? Bigger than half pi or smaller than half pi, either way is fine. Half space is nothing but the angle. It's this kind of angle bigger or equal or less than half pi. But as long as you can define angle, you're fine. Angle typically defined in inner product. All right, so this guy, I hope you can think about this as a half space in. So this should look to you no harder than this one. That's the requirement I somehow ask you to think this way. Because when you see this, you're scared. You will just say, this is not my type of problem. But in nature, this has exactly the same thing as this one, okay? In terms of the nature of the problem. Well, that's a affine set and a linear set and a linear function. Now let's talk a little bit one more step, which is a quadratic set and the quadratic functions. Quadratic functions. What are quadratic functions? Let's say I have fx, maybe in your undergraduate class, your baby type of class, you will write all the elements out, right? To me, these are the same, okay? Everything by default can be a vector, and the vector may be even a function, okay? So it doesn't matter. So let's say this is finite dimension, this is that. This will be a quadratic function, right? This will be a quadratic function. Or is this quadratic function? No, sorry. 2 minus 3x1 x2 squared. Is this a quadratic function? It's not. The maximum order of these variables is a lot bigger than 2. All the individual elements is not. So this is not quadratic. So those kind of things are quadratic. And we can write quadratic function in terms of vector matrix, right? So the most standard form can be written like this. The most general form can be written like this. It can be some constant. By the way, this is x is in Rn, x1 all the way to xn, and f is a mapping from Rn to R. So you gave me a vector, I tell you a number. In this class so far, we don't talk about too many, so vector valued functions because we are trying to do optimization. So we have a cost function which are take values in R. The most general form is this. This is the linear term. This is the quadratic term. I'm going to ask, hold on, maybe Yinghan again. For this problem, let's say just this one. Do you know what, I'm not asking you A is too hard, B and the C value. All zeros. Why? There's no linear term. There's no constant term. They're all zero. It's only.
Because there is no first order term.
Yes, exactly. There's no first order and no zero order term. Okay, good. So you know how to do the mapping. Again, even for quadratic function, we can also do homogeneous coordinate. It's the same way. If you define x tilde as x and append that x with this becomes Rn by 1, n plus 1 vector, right? Then you can write it like this. If I want to write it down, it will be f x tilde, then becomes, this is x1 transpose times a, this is half b c times, times x1. And this is my x tilde, this is my x tilde, this is my a tilde. Well, you can check this is fine. So overall, you will have x transpose ax, this x tilde transpose, right? So you have a standard quadratic function without a linear and a constant term. You can always do this by introducing homogeneous coordinate. So sometime we will directly focus on this form. If it's not this form, you can make it to this form. All right, let's take a break. Okay, let's continue. I think it's very hard to focus in the afternoon to for this kind of math. Well, I don't think this is math. It's just a little bit dry without any connection to real life. But I think some people enjoy it, right, Liuben? I think you enjoy this kind of symbolic discussion. So here I have another typo. Some people tell me after class, this is a transpose, of course. Otherwise, a B is a column vector, okay? It's not transpose, it doesn't make sense. I have a lot of typos to pay attention. So for quadratic function, if you think about this as a quadratic function, I say this condition, f(x) is a quadratic function is a positive semi-definite. Oh, sorry, if it's always bigger than 0 for any x. Yangxin, what does this mean? The function is, what does this kind of function called? It's a special name for this kind of function. Positive semi-definite. Okay, positive semi-definite doesn't mean, well, we all learn positive definite or positive semi-definite from matrix, but more fundamentally, those are for functions. This is exactly a definition of a positive semi-definiteness. If I say, right, we define Lec11 function, that we define this, right? When we introduce Lec11 function theorem, we define this pretty carefully. If I say f(x) bigger than 0 for all x not equal to 0 and f(x) equal to 0 for x equal to 0, this is a positive definite. Is that true? And if f is a symmetric, if f is a quadratic function represented by this, then because all the behavior of f(x) is completely characterized by the matrix A, so we call A is a positive self-definite. If the quadratic function is defined, it's positive semi-definite function. So So the most baby or most elementary definition should be function is positive semi-definite or function is positive definite. When quadratic function case, then the function is completely characterized by a matrix. So when in that case, the matrix is positive semi-definite, matrix is positive definite due to the representing function is has the same property. Okay. I think that's a few remarks. Again, we say quadratic functions. Then, as I mentioned, all the sets are represented by level sets. 等高线是吧？你说的这叫 level sets or sub-level sets or super-level sets of functions. So when we say quadratic set, are typically represented by quadratic functions. For example, I can say, for example, let's say this x1, x2 equal to 1 or less than or equal to 1. Well, that's a quadratic set because the level set of a quadratic function. Or x1 squared less than 2. This is a quadratic function. There's a special quadratic function that are super important for us, we're more familiar with. It's a ball and the ellipsoid. How to write down the expression for a ball? Johan. A ball, yeah, not sphere, a ball in Rn. Let's say in Rn. So will be x belong to Rn such that ball means what? Define ball is like distance from to the center. Let's say x is the center of the ball. Okay, all the points need to be distance less than RC. Let's say that's a ball. Typically, I can write square as well. It will be the same. Sorry, there will be R squared. So is this a quadratic set? Yes. Because this equal to, you can think about fx like x minus xc transpose times fx minus xc minus rc squared. That's my fx. And fx less than or equal to 0 is a sub-level set of this fx. Because this fx is quadratic, so the ball is a quadratic set. Okay, that's the ball. Ellipsoid is a linear transformation of a ball. Basically, that's what it means. If you write it down like this, it's a ball, then I can write the ellipsoid. I can tell you I will be x minus xc, the center of the ellipsoid, transpose times p inverse x minus x transpose less than 1. That's typically the ellipsoid. When we define this p need to be s plus plus and positive definite, so that it can have an inverse. There are different ways to represent ellipsoid. I think you can look online. I don't think that's that important. I just want to tell you, ellipsoid is also a quadratic function of x, and it's a quadratic set. Why this is important? If I say a constraint, let's say I want you to minimize some function, and the value, the variable you can take is within some ellipsoid. Fine, right? If I just tell you that, I think maybe there's a manipulability ellipsoid. There's a lot of ellipsoid, right? An ellipsoid, you say, look for a point within the ellipsoid such that minimize certain things. And you will know, okay, that ellipsoid gives me a quadratic constraint. And that quadratic is convex, okay? So I want you to somehow make connections of between the math and the geometry, so that you can think abstractly a little bit easier. Because once you have a figure in mind, it's easier for you to think. Ball and all these things are the same. It's the same thing, like I said, you should know this kind of thing is a half space in your mind. Those complicated stuff, you think, oh, that's an ellipsoid, that's a quadratic, that's a convex constraint. Oh, I haven't introduced what's convex yet. That will be the next concept. I introduced affine function, quadratic function, affine set or linear affine set or quadratic set. There's many of variations of them. We don't need to enumerate all of them. The next bigger class of functions, let's call that convex set and convex functions. Let's first give a definition of convex set. I think many students know about this. Even in my undergraduate class, I sometimes introduce this a little bit, but not always. So Yinghan, you have learned this before, right? In my undergraduate, in my modern control class, or not? You forgot, where did you learn? But you know, okay, good. So what is a convex set? A set, here the S is not a symmetric matrix, it's just a set, okay? A set S is convex if, in words, in plain English, is any line segment stays in the set. Okay, that's basically what it means. If you take any point in the set, the line segment is a line connecting x1 and x2. If you take, this is x1, right? This is x2. If you draw a line segment, and this line segment has an expression like this. As alpha equal to 1, that will be x1. Alpha equal to 0, that will go to x2. In between, alpha in between 0 and 1, that will covers the line segment, right? This can be written as alpha x1 plus, let's say, alpha 1 x1, alpha 2 x2, where alpha 1 plus alpha 2 equal to 1, and alpha 1, alpha 2 bigger or equal to 0. So this thing is the same. Because you require alpha between 0 and 1, right? I can also write, I can define this guy, 1 minus alpha, as another variable, alpha 2. So alpha 1 plus alpha 2 is 1, alpha 1, alpha 2 bigger than 0. And this is called a convex combination of x1 and x2. Okay, some terminology. All right, so if a set is convex, let's say I have a circle. I don't think the way I draw it is convex, but let's assume it's a circle. If you take any point in the set, you draw a line segment, it stays in the set. So this guy is convex. Maybe this guy is convex or not, Yonghan? No. If you pick a point here, you pick a point here, it contains the line segment, right? So this part is okay, but if you pick point here, it goes out. So it's non-convex. The set is non-convex. Well, just to make sure that it's aligned with your intuition, this set is indeed non-convex. When define convex set or work with convex set, the convex combination is really important. Just define for 2 points, just like that, alpha 1 x1 plus alpha 2 x2. If I have k points, the convex combination is just alpha 1 x1 all the way summation all the way to sum all the way to alpha k x k, the summation of all the coefficients are 1, and there has to be bigger or equal to 0. So this gives me the convex combination. Suppose I have 3 points. What's the convex combination of all the convex combination? Let's say this is one of them. All the convex combination, for example, this line segment is a convex combination, right? For this case, 3 points, right? 3 points. So I have alpha 1, x1, alpha 2, x2, alpha 3, x3. That's the point can be written as a convex combination is like this. So this line, let's call it x1, x2. In this case, alpha 3 is 0. These two are doing this interpolation. Okay, so that we can have this, we can have this, and also we can have all of this. If I have a convex combination of all the convex combinations actually make up this entire triangle, interior of the triangle. I hope you can argue that. If I have 4 points, that will be the whole thing. That's the entire thing. Convex Hall, okay, of any set is all the convex combination of points in S. Suppose I have a non-convex set like this. If I say I want to contain all the convex combinations of the point in S, then all these things are there. So of course, these are here. If I know these two guys, when you draw a line, these are convex combinations of the points in S, but it's not contained in S. It should be contained in the convex Hall. So this guy in and all the things, eventually you will have this kind of set. Okay, it's the smallest set, convex set contains the original set. Typically, it's the smallest convex set contains the original set. Okay, that's a few terminology. Let me recall, if I have x1, x2, let me review that later, okay? Let's introduce another thing which is called cone. Geometry is really important because it can help you think about abstract things in a geometric or picture way. We think about convex now. Let's think about a little bit more restrictive set, which is a cone. A set S is called a cone. When you think about cone, you think about what? Ice cream, right? Cone, ice cream, that's the cone. But how do you define the shape of ice cream? What are the mathematical foundation or nature for being a cone? Is actually, you take any point in the set, if you scale it positively, if you scale or shrink it, the its length, you always contain the set. For example, if I have a ray, this is the origin, okay? By default, this origin will always has to be contained in the cone. So this line or this ray pointing to one direction, this is a cone. Because if I pick arbitrary point, let's say x1, I scaled it, maybe half x1 is here, 2x1 is here, is always on the line. Okay, so this is a cone. And also, you can have a sector like this, right? Xunhan, is this a cone?
Yes.
Okay, first of all, I want to ask you, is this a convex set?
No.
It's not convex, okay, this is not convex. Is this a cone? Liu Ben, you think it's a cone or not? Oh. What? You pick an arbitrary point, you scale it. Does that contain in that? Well, I think it's a cone. Why not? It's not cone. If you pick any point in the set, you scale it, it's always there. 当然有原点了 OK.
我以为它不是。
Okay, yeah, it's okay. Anyway, suppose this is the origin, okay? It's a cone, but it's not convex. So cone doesn't need to be convex. It's a cone. Okay, we have a convex combination. We also have a conic combination. That's typically a basic building operation of build up a cone. For example, I have 2 points. Let's say I have 2 points, x1 and x2. With alpha 1, alpha 2, the convex conic combination is just the same. Alpha 1 x1 plus alpha 2 x2, where alpha 1, alpha 2 are all non-negative. There's no additional requirement about summation of alpha 1 equal alpha 2 equal to 1. There's no that. That becomes a conic combination. If I have multiple, that's a cone of x1 all the way to x, let's call it xk, then that will be nothing but summation alpha I xi. So all the points of the following form that can be written as summation of alpha I xi, where alpha I bigger or equal to 0. That's the conic combination. If I have this line, these 2 points, let's say x1, x2, I can generate. This is my 0. Okay, this is my things. Actually, the conic combination contain all the conic combination will be just this one. Okay, all right. Now, cone that is convex will be called a convex cone. For example, I can show you another cone that is really non-convex. It's like your ice cream, but weird-shaped top ice cream. Is that fine? You think about this in space. So the top is somehow you bite it already, so it's not a perfectly a convex thing. This is a non-convex cone for sure, right? If I want the cone to be convex, of course, can be equivalently, that is a set contains all the conic combination of a point in the set. If that's the case, then will be a convex cone as well. That's a 2 definition. You can show the cone is convex by definition of convex set. Or if you think it is a set that contains all the conic combination. I didn't say convex combination. Conic combination, that's fine. For example, in this case, this example, if I look at convex combination of these 2 points, that will be this sector, right? If I like to say convex conic combination of these 2 points, it would be this sector. Does this union of these 2 sectors contain all the conic combinations? No, because in other words, you also need to contain all the other things. So eventually it will become the entire R2. Okay, so whenever it contains all the conic combinations, it will be a convex cone. I'm telling you too many things. Some of them are not that useful, some are useful. One thing that are pretty useful, especially for the next class, is the so-called positive semi-definite cone. Yinghao, what does this mean again? Set of all the positive semi-definite matrices. So it's the set of all the matrices. Now I ask you to prove this set is a cone. Does matrix has to be related to cone? Doesn't matter. It's as long as it's a set, I can define whether it's cone or not. So then I want to say, is this a cone, first of all? How to prove it's a cone? So then what's the definition of cone? So let's pick arbitrary point in the set. So let's say I pick arbitrary, pick A in the set. All I need to verify is what? Lambda A, I need to stay in the cone, right? Where lambda need to be for any positive or non-negative number. Is that true? If A is positive semi-definite, does lambda A positive semi-definite? Yes, whenever lambda is whenever lambda is non-negative. Okay, so this of course tells us this guy is this. So lambda A belong to this set again. So at least we show S and star now it's a cone. But I didn't say this is convex or not yet. So now I need to tell you, or we need to argue through this cone, not only a cone, it's a convex cone. How to prove it? By definition, okay, you know everything is by definition of convexity. So now any line segment need to stay in the set, right? So we have, let's pick now, pick arbitrary matrix, let's say A and a B in the set. Oh, that's wrong. In the set. I need to show for scalar alpha, A plus, in this case, I just say 1 minus alpha is fine, right? 1 minus alpha B for any alpha between 0 and 1, this guy need to stay in the set. Line segment need to stay in the set. The set is what? Right? So I need to check this, guy, right? If that's true, then, so sometimes I write it wrong, right? Definitely, is that what I mean? Yes. Okay. Sometimes I change, I'm writing too fast. Okay. Let me define. So, sorry, define Sn plus equal to S plus n, all right? So all the notations are good. So we don't need to correct. If I have problem, that's okay. So can you prove this step? Is this true? How to prove this? I want you to prove now what? All you know, A is positive semi-definite, B is positive semi-definite, alpha is between 0 and 1. And I want you to show this alpha A plus 1 minus alpha B is positive semi-definite. How to prove? So how to prove it? By what? By what? By definition. I just asked you to prove something is positive semi-definite. So by definition of positive semi-definite matrices, you should be able to prove it, right? There's nothing fancy. You just need to know. I ask you whether this is positive semi-definite matrix or not. You just need to check whether it satisfies the definition of positive semi-definite matrix. You don't need to overthink. How to prove a matrix positive semi-definite? That means X transpose times alpha A plus 1 minus alpha B X has to be non-negative for all X. Is this the definition? Matrix positive semi-definite just means the corresponding quadratic function it defines as positive semi-definite. So this guy, I need to factor out that would be alpha X transpose AX plus 1 minus alpha X transpose BX. I know I know A and B are both positive semi-definite. So this guy is bigger or equal to 0. Because this guy is bigger than or equal to 0, this guy is bigger than or equal to 0, you have two bigger than 0 thing summed together, so it's always bigger or equal to 0. So that's true. So we prove it. What we typically write QED, right? Or some kind of sharp. Also, based on your homework, you yet to complete the homework, you're going to show whenever AB in that trace AB is bigger or equal to 0, that means the cone, this is a cone, right? This cone is acute. So you wouldn't be able to have this kind of cone. Sorry, maybe even bigger. You will have this wouldn't be the case. The cone will be the angle acute. Okay, you are going to show that in your homework. I think some students are familiar with it, so I'm a little bit faster than I should be. Okay, let me, where's it? Hold on. Okay, alpha 1 x1 plus alpha 1 x1 plus alpha 2 x2. Let's say x1 belong to Rn, x2 belong to Rn. Okay, alpha 1 x1 plus alpha 2 x2. I don't have any restrictions on alpha 1, alpha 2. This is called linear combination. Okay, linear combination. All the linear combinations generate a linear space. Is that true? The linear space spanned by this x1, x2. If I say alpha 1 plus alpha 2 x2, I impose some conditions. Alpha 1 bigger or equal to 0, alpha 2 bigger or equal to 0. So this is what you think about, right? This is a conic combination. It's a conic combination generated by these 2 points. If I say alpha 1 plus x1, alpha 2, x2, alpha 1, alpha I bigger or equal to 0, summation alpha I equal to 1, this is a convex combination. Generate a convex set or line segment between these two. Here I'm trying to prove this set is convex. So I need to test the convex combination. Okay, I hope that's clear. That's an important property. The positive semi-definite matrix, the set of this matrix set is a cone, is a proper cone. Well, next lecture will be useful. For now, it's just for you to get familiar with those some kind of a little bit rigorous discussion. If you want to prove that or prove something is convex, some set is convex, we come from definition, right? But sometimes you don't want to always prove things from the basic definition. There's some kind of a result you should be aware of. So intersection of possibly infinite number of convex set is convex. Okay, suppose you know polyhedron is that, right? So polyhedron is that H1 transpose X less than H1, sorry, H1. This is a convex set, by the way. This is a affine set, which is always convex. I have another one. This is another convex set. If I put them together, that will be H1 transpose, H2 transpose times X less than H1, H2. That's simultaneously satisfy these two constraints. That's the intersection of these two sets, because that will be convex, right? It's like this guy is convex, and the other one is convex. So the intersection is also convex. So we can also prove positive semi-definite cone is convex by thinking this as a intersection of uncountably many point sets, but I don't want to discuss that in detail today. All right, another basic, I think there's many. I don't want to go over all of them. So a fine mapping of a convex set is always convex. What does that mean? For example, suppose I have my E1. Yangxing, what this set is? What is this kind of set? Ellipsoid, right? Ellipsoid, 凸球, ellipsoid. Okay, we can write this ellipsoid equivalently like this as well. That's two different ways to represent the same ellipsoid. The center plus some kind of linear mapping of a ball, okay? So let's say a ball, as I mentioned before, is like X belong to Rn, X norm squared less than 1. That's a unit ball. And if I define the mapping Fx equal to P half X minus Xc. Suppose we define. So now I'm going to ask you, Hongbo, what kind of function is this function of X with respect to X? Linear, affine function, right? Affine function. Okay, good. That's a linear or affine function. Let's use them interchangeably. Then I can say, I'm not sure whether you can see that. E1, this is E1, okay? E1 is it's nothing but if I take the affine mapping F of this unit ball, that becomes E1. What does this mean? You plug any point in the ball, you apply this thing, that becomes a point in the E1. So E1 is essentially, you just take a point in the ball, then you do this mapping, it becomes a form of this. P equal to P half if we, let's say P is a positive, P is a positive definite. Okay, this P is not the P inverse we used before to describe it solid. It's just for simplicity, I use a P here. That's how I mean by taking a set, mapping of that set to generate another set. If the mapping, how to say, let me draw a figure. I'll skip the other one. Okay, so this is a ball. So all the X satisfied within this circle is the ball. If you take a mapping f dot, so all the point, and it will become like this. So a point on this point may be mapped to, after this mapping will be mapped to a point here. Okay, so every single point in the ball, if you take this function, it becomes another point, and that point lies in the ellipsoid. These two are the same. Okay, so what I mean is that if a set is convex, if you take a fine mapping of convex set, it will always be a convex set. Okay, there's another example. I don't want to discuss them in class. There's a lot of tricks. Typically, I'm not sure. Fuzhen spent the whole semester learning this optimization, only convex optimization. Yeah. Right. That's a very important training. But we go over these things very fast because I don't think you can do theory after a few lectures. So I just want you to know enough concepts, enough terminologies, and understand them, don't memorize them, so that you can become an educated user of tools. Educated user, educated is very important, okay? It's not like you don't know what's going on, just call the package. Okay, now let's, I think we have another 8 minutes. Linear set, linear function, convex, quadratic function, quadratic set. Now we introduce a convex set. Now we talk about convex functions. But the way I define convex function, I don't want to using the epigraph stuff that maybe Fuzhen just mentioned that. Let's just use the very basic definition. A function is nothing, a mapping, right? Maps from a point in the domain to, this is a real line, okay? It's called convex if they satisfy the following property, and this is the, I don't think the most general definition, but at least a pretty general definition. Roughly speaking, it's that, let me draw the figure, okay? So this is my x line. Maybe I have 2x, this x1, this is x2. By looking at this function, you should be able to tell, or somehow intuitively you can tell this is a convex function. But mathematically, how to describe it is that the function value, this is my x1, this is my fx2. Alpha, this will be a convex combination of these function values. Okay, so suppose this is the line. So they will be line segment like this. So as alpha increase, that's alpha increase from, let's say alpha equal to 0, that means you are at f2, right? This is alpha equal to 0. Alpha equal to 0, you're at f2. Alpha equal to 1, you're at fx1. So as alpha change from 0 to 1, the right-hand side is moves along the line. Okay, the right-hand side is a function value of the line segment here. So that means the function value always stays below the convex combination of these function values. Okay, so that's roughly the figure, the statement or the definition means. The function value always stays below the convex combination or the line segments of this the values of the two endpoints. Okay. The question I will ask you is the convex function need to be differentiable. Yangxing? No? Does the convex function need to be differentiable? Does the convex function need to be continuous? Well, I think I forgot. Okay, I think you need, well, convex function. I mean, the definition doesn't say whether it's continuous or differentiable. Okay, typically convex function is continuous. I think it's true. Okay, I may need to check. And it definitely doesn't need to be differentiable. Okay, it can be like, is this convex? How do you check? Pick any point. The value, the function value stay below that, convex. Or you mathematically or algebraically you verify this condition for arbitrary x1, x2, which is typically hard to do, but that's the definition. It's called strictly, not just convex, strictly convex, if the inequality sign becomes, if the less than equal becomes just strictly less than, strictly below. So for example, is this convex or strictly convex? Or non-convex? Hongbo, that's convex, right? Of course, it's definitely convex, but not strictly convex. You have flat area for which these two equalities, these two sides are equal to each other. Okay, and it's called concave if it's not, if the negative is convex. It's like the negative sign, so it's like this guy will be concave. You stay below the line segment, the concave will be stay above the line segment. Okay. And how to check a function is convex or not? There are a lot of results out there. I don't think we need to know too much about them, but at least you need to know two results that are really useful. One is, I mean, these are sequentially harder and requiring more and more. This is called the first order condition. The previous definition is basically zero order. I didn't require the function to be differentiable. But in case the function is differentiable, I can state that result in terms of first order condition, which is if it is convex, then the function value stays above, let's say stays above the Taylor expansion around x. What does this mean? So if you have a function like this, you can locally approximate this function by a linear function like a Taylor expansion like this, right? So this will be linearization around, let's say this is my x. So about around this x, the function value always stay above the Taylor expansion or first order. This is a affine or linear approximation of the function locally around x. So this needs to be true for all x and z in D. How do you, why this defines the convexity? This equality, this condition, if you can use this condition to prove this one. The proofs will be 15 lines of proofs. Maybe that's pretty, I don't think it's trivial. But I wanted to remember this, these are the first order condition. And let me finish this one. I also have a second order condition is the Hessian to be positive semi-definite. And these can be easily used to prove that. Okay, this proof is a little bit easier. Maybe I can put it as a homework. But and there's many other condition tricks. So this condition require the system not only differentiable but also second order differentiable. So it'll be stronger. So if the function is not differentiable, you can only use this to check. If the first order differentiable, you can use the second condition to check. If the second order differentiable, you can check the Hessian. Okay. So there's many other tricks we will talk about, or we won't go over the tricks. I think we will finish optimization next lecture. Let's continue our discussion on optimization. As I mentioned before, optimization is the key foundation for many engineering problems. Our goal in this class is to introduce optimization theory for you to become an educated user of existing tools and the packages. So you need to know some terminology about optimization. So that's why we introduced some linear algebra background. And last time I think we almost finished talking about the set and the functions. So the sets, the categories of the constraint set and the categories of function natures will determine the nature of the optimization. We will maybe point that out today. So let's continue our discussion. Last time, I think we stopped at convex function. There's different ways to define convex function. The most elementary or most important way is to define function, which is convex, only based on the function expression, but does not rely on the differentiability of the function. Okay, so this is basically this is the convex combination of these function values always stay above the actual function value at any critical point. Okay, we can look at this figure. That's the definition of convex. And there's many other tests that you can use to test whether a function is convex or not. Kind of a popular test, maybe most of you have heard of or have used before, is the second order condition, but that's really require the function to be twice differentiable at least. And in that case, the function is convex if the Hessian, okay, is positive semi-definite matrices. If it's positive definite, it will be strictly convex. If it is not second order, if it is not twice differentiable, then we can use the first order condition, right? Which is this one. This function value stay above the Taylor expansion around X. Look at this figure, right? If it's not differentiable at all, you should use the original definition of convex functions. Okay. There's many kind of examples of convex functions. I don't think I can list all of them. There's a separate class about convex optimization, which talks about basically all the tricks, theories to verify whether a function is a convex or not. And for us, it suffices for us to know at least for us to know some key important result. The first one is that all the fine functions, including linear, okay, all the fine functions are both convex and concave. I'm not sure whether I introduced concavity or not. Yes, concave means negative f is convex, right? So, for example, if there's a concave, then let's say, if we say the condition like second order condition, the concave means the Hessian is negative definite. Okay, for all x in the domain of the function. So because if this is a negative semi-definite, then negative f will be positive semi-definite. So basically, we only talk about convexity. We do not, because the concavity is very easy to define indirectly through convexity. Okay, so a fine function is both convex and concave. Okay, Ruben, how should we prove it?
By definition, plug this function into the convex combination and the concave combination.
Okay. You plug in, you can find out actually they should be equal, right? So
Yeah.
so it's or you can use the second order condition. You can take Hessian. The Hessian will of f will be what?
Will be 0.
Yeah. So it's always semi-definite. Okay, it's not strictly convex, but it's a concave and convex. All right. For example, the affine function can be written of this form. That's a function affine in X. I think we defined that before. We even define what we mean by affine or linear with respect to matrix variables or with respect to even a function. Okay, if the X doesn't need to be a scalar, even doesn't need to be a vector. It could be a matrix, it could be a function. I think we defined that before. Okay, I think we mentioned this before, right? This is a function. For example, this is a function of X, where X is a m by n matrix. Okay, and it's a matrix variable, so it's a maps from a m by n matrix space to a scalar. Okay, so this is definitely also a affine function of X. You can prove that by the definition of affine or linear. And if you write down element-wise expression, you can see that it's nothing but a kind of a linear affine function of its element. Okay, so this is also a affine function. You can think about this function as a function. I think this is a affine function of X, which is a matrix variable. Okay, affine functions are both convex and concave, and the quadratic functions is another very important class of functions that we often use, especially in robotics. Okay, and the quadratic function does not need to be convex. Okay, it is convex if and only if the quadratic term that defines the quadratic function, the quadratic term, the Q matrix that defines the quadratic terms or positive semi-definite. This can be verified by using the second order condition. Okay, so you can say the Hessian of this equals to, by definition, let me remind you, by definition, this is x1, 1, partial f, x1, 2. Sorry, not that. Partial squared, x1, x1, x squared, x1, x2, So you can see, assume that x equals x1 all the way to xn, which is in Rn. Okay, the Hessian of this quadratic function is a n by n matrix. This is an n by n matrix. So we can check whether it's positive definite or not. First of all, it is has to be symmetric if Q is symmetric, and this one will be actually if you derive it, it will just be Q. So based on the second order condition, Q is a positive semi-definite if and only if this quadratic function is convex. All right, so that's you need to check this second order term. Okay, and also some other tricks that I don't want to mention all of them, or some other facts. For example, all norms are convex. I'm not sure whether you still remember what the P norm means. For example, I can give you an example. The one norm of a vector, this is the case, okay? One norm means the x1 element-wise, okay? The absolute value of x1, x2, all the way to xn, okay? And the infinity norm is the max of k, xk, okay? and the p norm, or let's say 2 norm, let's say 1, 2, okay, infinity. That's the typical norm that we use in optimization, especially problem related to control. Xn squared, that's the 2 norm we I think we are familiar with, and the 1 norm and the infinity norm are also sometimes we use them quite a bit. Okay, and those are all convex functions, right? So these are convex functions of x. This norm is a convex function of x, and 2 norm is also convex function of x. If I have a matrix variable, and the matrix norm is also a convex function of that matrix variable, it's not affine anymore. Okay, and okay, that's I think. Oh, I think I need to mention a few other facts that are important, but are not listed in the notes so far. Let me mention that. So I think affine mapping of a convex function is still convex. What do I mean by that? Example, let's suppose my fx is convex. That's given. All right. Then I can define another function, which is, let's say, g of x, which I define it as, suppose this is convex. I define that as, let's say, that's a fx plus b. Okay. This will be also convex. Okay, that can be easily proved. I think that will be your homework. Okay, you're going to prove something quite a bit in the next few homeworks, maybe next 1 or 2 at least, related to optimization. And I don't ask you to design algorithms, but I want you to be familiar with the tools and techniques you need to formulate your problems, especially to formulate your problem in a way that are easy to solve using existing tools. Okay. Another thing is that another fact is pretty important. It's called pointwise, let's say, maximum of convex function is still convex. Is still convex. There's many facts. I only mentioned that something that are particularly useful. Maybe we'll use them later in this class, or I think it's pretty useful for in solving control problems, not in general optimization problems. Okay. What do I mean by that? So suppose I have 2 convex functions. Suppose both of these are convex. Then I can define another function. Again, let's call that g again. Let's call it g. Okay, I define it as what? As a pointwise maximum. So this is max of f1x and f2 of x. Then this g, then g is convex. I also may ask you to prove this, depending on whether I find other more important problems, or maybe I will ask you to prove this in the homework. But graphically, what this means is that I say, let's draw a figure. This is my f1. This is my f1 of x. Okay. I may have another one, which is f2. Okay, f2 of x. Both of these, based on the figure I draw, this is convex. All right, you can check by, I mean, I didn't tell you the expression, but based on the curve, it looks convex, right? A happy curve. Okay, what is the pointwise meaning? What about g function? So g function will be pointwise maximum. What do I mean by that? For its point, for each x, it's the max, it takes the value of max of f1 or x2. So for example, if I draw it a little bit more, okay. So for example, if I add this particular x, this will be f1, this will be f2. Because of this max, it takes the value of f2. So this will be my g x at this particular point. If you can think a little bit, generalize this thing, this one will be this. Okay, that's my gx. You can see that from the figure it's also convex, but you can also prove it based on definition. That's quite important. That's max of two functions. And we can also do a little bit more general. For example, I can say, suppose I have a function which is, let's say, suppose I have a function which is x parameterized by theta. Okay, suppose, let's say, suppose this is convex for each theta in, let's say, 1 and 2. Then if I define g of x defined as max, not only with respect to two functions, max over a continuum of intervals of theta, which the theta belong to, let's say, 1, 2, fx theta, this is also convex, okay? So you can think about this. We have an infinite number of f1, f2, f3. It's not only that, it's parameterized by theta. You over all of them, it's also a max over all of them. It's also a convex function. If I give you a concrete example, would be, let's say, f theta equal to, let's say, theta x plus b. Okay, for each theta, this is a linear function, which is convex, right? So I can define, so this is a max over theta belong to, let's say, 1, 2, theta x plus b. This is also a convex function with respect to x. So that's this property. And by somehow the dual or you can think about, well, that means you can, because of the concavity is defined in terms of convexity by taking a negative sign, you can immediately conclude because of this fact. And you can also say pointwise minimum of concave is concave. Oh, sorry. Pointwise minimum of concave function is still concave, yes. Okay, because you need to take the negative sign, maximization become minimization, and concavity becomes, convexity become concavity. Okay, that's also a quite important thing. For example, in the same function, if I define that x is mean over theta 1 and 2, theta x, this is concave. Okay, because a fine function is both concave and convex. If I take point as mean, I will get a concave function. If I take point max, I got a convex function.